All right, let's continue our discussion. So we're gonna talk about the other thing, which is quite a big topic here. So that's gonna last the rest of this lecture and also probably next lecture also. Right. So we're gonna talk about the what we call thermodynamical processes. Okay, so that's quite a long word. So what it is? So thermodynamical processes. So what does this mean? Oh, sorry. I didn't. Okay, so can you hear me now? Sorry, I forgot to unmute. Is it okay now? Okay, good. All right, thank you for letting me know. Okay, so we're gonna talk about thermodynamical processes. So what this means is just the way, essentially, the way that variables that we use to describe, property of matter change. Okay, so if we talk about gas, which we're gonna be talking about exclusively here. If we talk about gas, we're gonna talk about the way P, V, and T changes. Okay, and how we can exploit this change to build a heat engine, so that we can do some interesting stuff like driving a train, driving a car, making a refrigerator, something like that. Okay, so this is what we mean by thermodynamical processes. Just the way P, V, and T change for gas. Okay, so how do we describe this? Well, in order to describe, we need what we call a PV diagram. And it's the two-dimensional plot of P and V. So we have P in the vertical axis and then V in the horizontal axis. And then we can use PV equal to nRT again, right? So if you pick a particular point on this diagram, maybe here, then you can read off what is V by looking at the horizontal. Guys, can you turn off your microphone? Please turn off your microphone. Okay, everyone's good here. All right, so so we have a point in the PV diagram, and one point gives you the value of V and the value of P. So if you want to know what is the temperature here, right, you can use this equation to calculate. Right, so on this diagram, you can potentially calculate what is the temperature of this particular point. All right, and when you change from one point to another point, for example, a very simple one is to, for example, go from here to here. Let's say like this. Okay, so point 1 to point 2. So what's happening here? Well, to go from point 1 to point 2, the pressure stays the same, right, because it goes in the horizontal line. And the volume increases, right? So from V1 to V2, right? So this is a process, exactly what we call thermodynamical process, because what's happening here is that V changes, right? Even though P does not change, but V changes. So if V change, then the temperature will also change, right? So if you calculate the temperature at point 1 and temperature at point 2, you see that they are not the same, right? Using this equation, it's going to show something like that. Okay, so that's kind of like one very simple example of what we call the process. Okay, and the interesting thing is that there's many ways you can go from one point to another point on this PV diagram. For example, you can go directly a straight line like this, or you can increase the pressure first and then reduce and reach the same destination like this. Okay, so you're gonna have different what we call path on the PV diagram. So path essentially tells you how you move from one point to another point. Okay, so you're gonna have path 1 down here, you can have path 2, you can have path number 3, which is a little bit crazier like this. It's also possible, path 3. You can see that you can have infinitely many paths you can choose to go from point 1 to point 2. Okay, and different paths will have different properties, so we're going to be exploring a few different ways of moving along this PV diagram. Okay, and before we go any further, there's one thing which is very important, is the concept of work. This is not new, since all of you have learned the concept of work in your previous physics class already. So let me remind you briefly what we mean by work. So work in classical mechanics, which is what you learn in physics 1, is essentially just force times distance. Okay, roughly speaking, or you want to be more specific, like it has to be the force vector dot the displacement vector of that, but let's just talk roughly. So it's going to be force times distance. Okay, and what is force here? Well, imagine what happened when you have a gas container inside what we call a piston. So piston means the lid of the container can move. So this lid can move around. Okay, so it's not, like tight shut, not like a closed can or something. So this thing can move around. So let's say you have some gas inside here. Okay, and obviously this is gonna give you some kind of pressure, some kind of volume, right? So if the gas has some pressure, what does it mean? It means that if you hold on to the lid and then you let go of the lid, it will just fly away, right? So this is obviously, ignoring any external air pressure, right? So let's assume that we are in, like space where there's no air around us. The only source of air we have is in this container, right? It has some pressure, so you need to keep your hand pressed down onto this lid, otherwise it will just fly away, right? So in order to keep the lid stay the same, you need to apply some kind of force to, like hold it in place. Okay, so that's like how the force comes in this discussion, right? So now what we're gonna do is we're gonna compress the gas. Compress means to reduce the volume. Okay, that's what we mean by compression. So if you want to compress the gas, what do you have to do? Well, you have to put in the force which is a little bit larger than what is pushed out by the gas itself, right? You have to kind of win it a little bit, right? So if you increase your force a little bit, you can compress the gas. Maybe the gas become half the volume, right? But to move the lid from here to here, you need to apply the force in this way. And what you are pushing is the lid. So you have moved the lid by this much, delta x. That's going to be the distance. So you have force, you have distance. What you have here is work, right? So essentially what it means is that to compress the gas, you need to reduce V, the volume. That automatically means that you need to do some work in order to compress the gas. Okay, so how much work? Well, it depends on how much force you need to push and how much distance that you have pushed. So it can be calculated by this equation. Okay, but force by itself is a little bit hard to work with for gas because we are more used to the parameter of pressure. So instead of using force, we're going to rewrite force in terms of pressure. So what is force in terms of pressure? It's just the pressure times the area of the lid. Okay, so let me zoom in a little bit. So let's say the lid has the area A. Okay, like this. So it's a circular, so it's like pi r squared, something like that. But it's not so important what's the shape, exact shape of it. It's just the area A, right? So that's the force here. So force is just P times A, same thing, and then times delta x. Okay. And what is A times delta x? A times delta x is the volume of this section. So A times delta x is delta V, the change in the volume. Okay, so think about this carefully, how this is the case. So eventually you're going to have this new way of writing work, which is not force times distance, but but actually pressure times the change in the volume. Okay, so this is two variables, pressure and the change in the volume here. Okay, so F delta x becomes P delta V, which is very convenient because P and V are the two parameters that we use in the PV diagram. In other words, to find the work, we can write it in this way. It's actually just the area under the curve of P and V diagram. Similar to the area under the graph of force and displacement that you probably remember. So if you have F and X, and then you move like this, right? So the area under the graph, under the curve here, this area, that gives you work, right? And that's because W is given by F delta X, right? So now we just rewrite things to have it in terms of pressure and volume. So in a PV diagram, the area under the curve is the work done, okay? So for example, if you move from one point to another point on the PV diagram, maybe like here to here, right? So you have like V1, you have V2. So the work done is simply the area under this graph, which in this case is very easy because it's just a rectangle, right? So the work is this area. Work here is equal to P times the base, which is V2 minus V1, or P times delta V in this case. Okay, so that's what we have here. All right. Now you might have some question. If you have listened carefully to what I said, The work done that I discussed earlier, and that kind of leads to this equation of work equal to P times delta V. I'm talking about the way that we compress the gas, right? So it's the work done by us, which is, external being. So we are pushing the gas in. So the work done by us, that's what I'm talking about here. But, due to the convention, we will talk about the work done by the gas instead of work done by us. Okay, so work done by the gas is the opposite of the work done by us. So what's the difference? If you look at this picture here, the work done by us is given by the direction of the force, which is pushed by us. But in the point of view of the gas is pushing against this force, right? That's Newton's third law, action equal to reaction. So the gas is actually pushing it this way. So the work done by the gas is gonna be negative because the displacement go this way, but the force of the gas is pushing out. Okay, so the work done by us is negative of the work done by gas. So all of those might sound kind of confusing. That's okay. So we're gonna kind of write down our convention so that you can think about this later. Okay, so the area under the curve is the work, right? But work can be positive or negative. So how so? Well, you can go the other way. So for example, you can go from here to here, right? So you can go from V2 back to V1. So when you reverse the direction, then the sign of the work will be reversed. So let's write down the convention so that we are on the same page. All right. So we're gonna write it this way. So work is positive when the volume of the gas increases. Okay, this means the gas expands. And defining it like this is more preferable because it corresponds to a positive area in the PV graph. Okay, this is according to the way you calculate the area under the curve, from calculus or something. So when you go from left to right, that gives you positive area. So the work is positive, right? So we define the work to be positive when the volume of the gas increases. So that means the gas expands. Okay, so this is what we say for work to be the work done by the gas. Okay, which is opposite from the work done by us. Okay, so opposite means just the minus sign, right? So from now on, just to make things less confusing, when we talk about work, we're gonna always talk about work done by the gas. Okay, so every variable W that you're gonna see in the formula will always be the work done by the gas, which means if W is positive, then gas expands, volume increases. Right? If the volume decreases, then work becomes negative. So this means V decreases. So that means the gas is compressed. Right? So this is a very nice way of remembering like whether W has to be positive or negative. You just look at how the volume changes. Right? If you expand the volume, then W has to be positive. If you compress the volume, V decreases, then W is negative. Okay, so this is very important because if you mess up the sign, it will make the calculation also wrong. Okay, so this is work. Another thing I want to talk about is the concept of internal energy of gas. And that's going to be a little bit abstract, but it's important, so we need to talk about. So the next thing is the internal energy of gas. Okay, so what are we talking about here? So in, let's say, a box that contains many molecules of gas, even though most of the time we don't see the gas molecule, we know that it's there, they are there, and they are not standing still, they move around in a random fashion, so we don't know which way each molecule is moving, but we can calculate actually the average. That's what we're going to do here. Okay, so the internal energy of gas, we're going to use the symbol U to indicate that. So what is internal energy of gas? Well, U is simply the sum of the energy of each particle of gas. Okay, so let's say we have n particles, right? N can be a really large number, like 6 times 10 to the 23 particles or molecules, something like that. Right, so you just add the energy of each one. So we can write it in this way. So U is simply the summation. Okay, you add all of them. The kinetic energy of each particle, right? So EK is the kinetic energy. Sub I is just the EK of the I particle, right? The first one, the second one, third one. You just add this up until you exhaust all the particles in the system. Right, so this is the kinetic energy. Right. So the kinetic energy of each particle, well, is simply going to be given by 1/2 mv squared. Right. So some particle will move a little bit faster than the other one. Well, again, that's totally random, right? But we're going to assume that it's random, but there's an average value of the speed that the particle is moving. So we're going to say that each particle will probably be moving with this much kinetic energy. And V bar here is the average speed of each particle. Okay, so we're going to replace, the fact that some particle move slower, some particle move faster by just a single, average speed, which is V bar. So that means I can write U. Well, since now that every EK is replaced by this, which is the same for every particle, then I can just write U equal to N, which is the number of particles, times 1/2 m V bar square. Okay, something like this. All right, so now comes the thing that unfortunately I cannot, go into any more detail about like how we can derive this. There's a theorem which is called the equipartition theorem, which is beyond the scope of our class here. So equipartition theorem is the theory that relates the average speed to the temperature of the gas. Okay, so I'm gonna just state the result. So this one you probably need to forgive me by not proving it because that's gonna be the whole other course which we don't have time for that. Okay, so equipartition theorem is relating V and temperature all together. So it's gonna say that 1/2 mv bar square is actually gonna be equal to 3/2 kBT. Okay, so again, I apologize for not being able to prove it in this class, but this probably you have to just trust me that this is the case. Okay, so what is Kb? That's the Boltzmann constant that we talked about from last week. T is the absolute temperature. Okay, again, it's in Kelvin, right? So this theorem relates the velocity or the speed to the temperature. Okay, so from doing this, we're gonna arrive at the formula which I kind of do a direct substitution. So it's gonna be 3/2 N kBT. Okay, so while I didn't prove this result to you, this is actually a pretty important formula to know. Okay, so what does it say? It says that the internal energy of the gas depends only on temperature. Okay, that's very, very important. And we're gonna talk about the implication of this later on. Okay, so I'm gonna write it down again that the internal energy of the gas U depends only on temperature. Okay, so if you know the temperature, then you know the internal energy of the gas. That's going to be important later on. Okay, so now we have kind of two things that we talked about already. U, the internal energy, and if we go back here, work, which is P delta V. Okay, the last thing we're gonna put into all of this is Q, which is again the same old Q, which is heat. Right. But now that we have introduced the variable U, which is the internal energy, we can think about how Q is related to all of these. Okay, so you can consider like how you can increase the internal energy of gas. So let's say you have again a container of gas, right? And let's say you make it such that it's thermally insulated, so there's no heat flow in or out. So Q is 0 in this case, right? So maybe it's made from, I don't know, Teflon or something like that, which doesn't allow heat to flow in or out that easily. Okay, so let's say you want to increase the internal energy of this gas. So what can you do? Well, Q is 0, so the only way you can do is to compress the gas. So if you compress the gas, right? So what does it mean? Well, it means on the PV diagram, you reduce the volume. So maybe you start here and then you go here. You reduce the volume, right? So the work done by the gas, because you reduce the volume, is negative, right? So in this case, work is negative number. But your common sense says that if you do something like this, then the internal energy of the gas must increase, right? Because if you look at the gas is being compressed. There's some work being done here, and work gonna get converted to kinetic energy if you remember your physics 1, right? So by doing this, you should increase the internal energy should increase when W is negative, right? U should increase also means T should increase. And that kind of makes sense if you look at this diagram, right? You start here at point 1, and then you go to point 2. You can also, just for the sake of argument, assume that the pressure is the same, right? So instead of this arbitrary line, I can use like horizontal line here. And I can go from V1 and then compress it to V2, right? So at this point, I can calculate T1. This point, I can also calculate T2. But if you remember PV equal to nRT, right? The lower the so if you calculate sorry, let me say that again. So if you compress the gas, then T should increase, right? So then I can write something like this. Delta U is actually equal to minus W. Because when you compress the gas, T should increase. Delta U is the change in the temperature. So T would be higher, so delta U is positive, right? But you need positive number since W is negative, so you need like a negative sign here. So this is the first thing that we can kind of like play around with. The other way to increase U is to not do the work, but allow some heat to flow in. So if you have like another container, and then you don't do any work, means you don't change the volume, right? So you don't touch the volume. If you let some heat flow into the gas, delta U also gonna be increased, right? So Q is positive when you have some heat flow in. So in this case, I can write delta U equal to simply Q, right? So heat flows in, gonna increase the temperature, and hence increase U. So you can see that we have two ways of increasing U, the internal energy, right? By negative, by minus W or by plus Q. So altogether, this can happen at the same time. So we arrive at what we call the first law of thermodynamics. So that means if we combine these two ways of, changing U, it's gonna be Q minus W. Okay, this is the first law of thermodynamics. So let me remind you again, like what all these variable means. Delta U is the change of the internal energy, right? So that's essentially the change of internal energy essentially, since internal energy depends only on the temperature, so the first variable delta U is essentially gonna reflect the change in the temperature. Right? So if you have any change of the temperature, you can be absolutely sure that the internal energy is being changed. And that can happen in two ways. First is from heat flow, right? You heat up the gas, then it's gonna have more internal energy. You cool it down, you lose heat, the internal energy gonna reduce. And then it can also be from work. And this is again work done by the gas. And you can see now why defining the work done to be by the gas in this case makes sense. Because if the gas were to do some work, it needs to spend some energy, right? It needs to take some, store energy and then, convert it to work. And where does that energy come from? Well, it's coming from internal energy here, right? So if the gas is doing some work, the internal energy has to reduce, right? Provided you don't have any heat flow, right? Because otherwise the energy is not conserved, right? So in this case, we have this, which is called the first law of thermodynamics. And it's another way of stating a very important law, which is the conservation of energy law. Okay, so the first law of thermodynamics is just another way of saying conservation of energy. Again, how so? Well, it just means that if you have some kind of gas like here, if there's some heat flow into the gas and the gas does not do any work, this energy has to go somewhere. And the only place it can go is to change or increase the internal energy. Okay, so you cannot have heat flowing into the system does no work, and internal energy does not change. That's the violation of conservation of energy. Okay, so the first law of thermodynamics kind of makes sure that all the energy is conserved. Okay, so by looking at different processes, so we have a few minutes left. Maybe I just do a preview on what we're going to talk about next time. So we're going to talk about like how different processes going to have different value for like Q, W, delta U, all that stuff. So for example, we're going to talk about the process where we move around the PV diagram and keeping P, the pressure, constant. So let's say we go from here to here, 1 to 2, okay? So going from 1 to 2, P does not change, but the volume changes, right? So in this case, we can calculate directly what is the work done by the gas. So W is the work done by the gas. So W is essentially just the area under the curve, so it's here, right? So that's W. So W is just P times V2 minus V1. Okay. So usually W is very easy to calculate because whatever the graph is showing, you just calculate the area under the curve here. So the next thing we want to calculate is the change in the internal energy. Okay. And this is where the fact that U depends only on temperature becomes very useful here. So if you remember, U is simply 3/2 N kBT, right? So N is the number of molecules, Kb is the Boltzmann constant, so it's just a constant, but it depends on the temperature. So delta U is just 3/2 N Kb times the change in the temperature. Okay, so what's the change in the temperature? Well, it's the temperature at the final point, T2, minus the change in the temperature of the initial point, minus the temperature of the initial point, which is T1. Okay, so T2 and T1 can be calculated using PV equal to nRT. Right, for example, T2 here is simply using this equation, okay, P, we only have one P, times V2 divided by NKB, or small nr. Well, just to make things kind of consistent, I'm going to write the other formula, which is big N kBT. Okay, so T2 can be calculated. T1 can also be calculated. So T1 is PV1 divided by NKB, right? So you can calculate T1 and T2. So the difference, T1, T2 minus T1. So let me write it down here. So delta U is 3/2 NKB. Delta T is just T2 minus T1. Right? So you can just subtract these two numbers from each other, and then you can get delta U. So the interesting thing here is that to calculate delta U, you only need to know the temperature at the end point. Okay? It doesn't matter how you move from 1 to 2. For example, you can move from 1 to 2 like this. Okay? So the pressure is no longer constant, so it's going to go up and down, something like that. Right? In this case, the path is different, but the end point is the same. So T2 and T1 has the same value. So if T2 and T1 has the same value, then the delta T also have the same value. So no matter what path you choose, delta U is always the same. And that's very important. And I'm going to write it down here. Delta U is independent of path. So no matter what path you take, as long as you start from 1 and then you end up at 2, you're going to have the same delta U. But what about W? W depends on the path. Because different paths going to give you different area under the curve. For example, the upper path here, when you calculate the area under the curve, you have to count also that green area, so everything. So W, because it's the area under the curve, is not always just V2 minus V1. It's V2 minus V1 because initially we choose the path to be a rectangle, so it's just a straight line. So the area is given by this, but that's not generally true, okay? So delta U independent of path, but W, which is the area, do depend on path, okay? Very important. It depends on how you move from one point to the other point. And then the last thing we're going to calculate is what is Q. Because by moving from one point to another point, you also have the possibility of absorbing heat or releasing some heat, right? But Q by itself usually is very hard to calculate directly. So that's why the first law of thermodynamics comes into play, right? So from delta U equal to Q minus W. So by inverting this equation a little bit, Q is just delta U plus W here, right? So this is calculated from the area. This is calculated from the change in the temperature. So from these two known variables, then you can calculate Q. Okay, so usually Q is the last thing that you can calculate because it's easier to calculate W. It's also easier to calculate delta U. So that's kind of like the general flow of this kind of problem. And the last thing I want to mention is that since W depends on the path, delta U does not depend on the path, right? So that means Q here also depends on the path. So depending on how you move from point 1 to point 2, you can absorb a lot of heat or you can absorb a little heat, right? That's possible depending on the path that you choose. But again, delta U here depends only on the change in the temperature, which is independent of the path. And next lecture, we're going to see a lot of example building upon this principle, okay? So that's the end of today's lecture. So I will see you guys on next Monday. Okay, so take care and I'll see you later.